All right, let's go ahead and do an example of a buffered solution. We're going to start off just by calculating pH values of buffered solutions, and then we're going to look at what happens when you add either acids or bases to them. And so copy that down for just a second. Okay, we're dealing with acetic acid here again, so I'm going to make myself just a little note. Ka is equal to 1.8 times 10 to the negative 5. Okay, here's my problem. It says find the pH. Again, we're worried about pHs throughout all this. Find the pH of a solution where I've got 50 milliliters of 0.5 molar sodium acetate mixed with 25 milliliters of 0.25 acetic acid. Okay, I already know from the previous problem that my reaction, whenever you just have the salt added to it, that Na doesn't matter, so all I have here is HC2H3O2 dissociating into hydrogen ions and acetate ions. The only difference is that I'm going to have a starting concentration of acetate ions here. Okay, so it's kind of like the problem that I already did, except for now I am given different volumes of each, different milliliters of each, so I've got to figure out the concentration. Let's figure out first. Let's start with acetic acid. I'm going to do this down here so I can have room to set up ice table up here. Acetic acid, HC2H3O2. In order to figure out that concentration, I want molarity, so I want moles per liter. I can use the information that they've given me here to find moles. And that number of moles, actually when you're dealing with buffers and you've got milliliters and molarity to work with, you can just take the milliliters, which is 25 milliliters, and I can multiply that by my molarity, which is 0.25. And since I'm not converting this into liters and I'm leaving it as milliliters, it's going to give me my answer in millimoles. You can work in millimoles with buffers. So I can just go ahead and multiply those together. That's going to give me 6.25 millimoles of acetic acid. Now for the acetate ion, I'm going to take that number of milliliters, 50 milliliters, multiplied by that concentration, which is 0.5, because I can take that 0.5 as my concentration of acetate ions, because this is a ionic salt, so it's going to completely dissociate. 50 times 0.5, that gives me 25 millimoles of acetate ion. Now I want concentration here so that I can figure this out with equilibrium and my ice table and all that stuff. So if I want concentration, then I can just go ahead and take my number of millimoles, 6.25 millimoles, and divide it by my total milliliters of solution. So 50 plus 25 is 75 milliliters. That's why I can work in millimoles, because if I do millimoles divided by milliliters, you would get the same answer if you did moles over liters, which would still give me my molarity. So here is 0.083 molar. That is my initial concentration of acetic acid. And to find my concentration of acetate ions, it would be my 25 millimoles over 75 milliliters of the whole solution. That gives me 0.33 molar. That's my starting concentration of acetate ions. From there, it's the same as what we have done before. So plus X 0.33 plus x, 0 plus x, x minus x, 0.083 minus x. Okay, solving for x, and I gave you Ka values. So x equals, and you should go back and make sure that you can calculate this properly, but, using your ice table stuff. So x is equal to, and again, get in the habit of writing this. X equals my hydrogen ion concentration, which equals 4.5 times 10 to the negative 6. Negative log that, my pH is 5.35. Okay, now, you can do it equilibrium way with buffered solutions. But with buffered solutions, there is a cool new equation that we can use and work with. It's called the Henderson-Hasselbalch equation. It only works with buffers. It doesn't work with stuff if it's not a buffer. And again, buffers have weak acid and a conjugate base of that weak acid, or a weak base and its conjugate acid. Both have initial concentrations to start with. So here's the equation. We went through for number 3 here, and we calculated pH using equilibrium and concentrations, and we went and found millimoles and all that stuff. Another way that can be done, an alternative way, and it's kind of a shortcut, easier way. The pH is equal to pKa, we'll talk about what that means in a minute, plus the log of the concentration of the base over the concentration of the acid. Now, what in the world does pKa mean? Well, we know that pH is the negative log of the hydrogen ion concentration. So pKa is just the negative log of Ka. So if we take a look at our previous example, number 3 that we just did, if I use the Henderson-Hasselbalch equation to solve for that, I would take pKa, which is the negative log of my Ka value for acetic acid, which was 1.8 times 10 to the negative 5, plus the log of, and it's the concentration of the base over the concentration of the acid, and we're talking about initial concentrations here. So 0.33 is my initial concentration of acetate ions, 0.083 is my initial concentration of acetic acid. So my base is the acetate ion, so that's 0.33 over 0.083. And I want you guys all to kind of practice plugging this into your calculator, make sure that you get it all plugged in correctly. You do get 5.34, which we got 5.35 in the previous example. That's considered close enough to be to work well. So you should also know when you're plugging in the concentration of the base and the acid, when we calculated this concentration, we took the millimoles, which was 25 over 75, and we took the millimoles, 6.25, divided by 75 over here. If I were to just plug those in, those expressions, then the 75s cancel. So when you're using Henderson-Hasselbalch equations, you can also plug in millimoles instead of concentration. So if I did the log of 25 over 6.25, it would give me the same ratio as this would. So you don't have to go through the whole process of solving for concentration. You can just solve for millimoles and plug those in. When you're dealing with buffers only, you can use this equation to solve for pH.